All right, CNT140, we're looking at Chapter 4. We're continuing on talking about horizontal connections. They remind us that most of our horizontal connections in our standard install uses UTP cable, absolutely. As we learned from 120, inexpensive, good performance, kind of easy to terminate, etc. One of the reasons we use it. As we started using Unshielded Twisted Pair, though, it became obvious that different types of twisted pair perform better, worse, etc. So they had to come up with a way to designate this one could perform to this level, this one performed to this level, and so forth. So they start coming up with these levels. Eventually, what we start learning of is category 3, 4, 5, so forth. And what happened, okay, here real quickly, I'm going to take a quick side step. Actually, I'll finish their thought here and I'll take a quick side step. Most things today we use category 5E, 6, etc. because they perform better. Our performance in the cabling is dependent upon frequency. Okay. If we think about how, if we want to send more data through a cable per time, we can't reach over and grab the volume knob and crank it up to 7, 8, or 9. It doesn't quite work that way. As I want to start putting more bits through per time in my cable, what happens is I need to start increasing the frequency. The higher the frequency or the greater the frequency band, the more bits I can send through per time. The only problem is when I start increasing that frequency, what happens is the performance out of the cable changes, and one of the ways you rate the performance of cable is with a number called impedance. Real quickly, if I were to look at, here's a sample impedance calculation of a circuit, okay, and the impedance, the formula is actually Z equals square root of R squared plus X squared total. What it amounts to is the total reactances plus the total resistances, the square root of that gives me the impedance of my cabling. Well, if you remember when we started learning twisted pair, all this twisted pair cabling should be 100 ohms. I'm going to make this go away for a second so we don't freak you out. Okay, all my twisted pair cabling should be 100 ohms. If I start connecting 100 ohm twisted pair cabling to 150 ohm twisted pair cabling, I have an impedance mismatch. And what will happen is, as the signal goes from the 100 ohm to 150 ohm, we're going to start getting reflections, and we're going to start getting attenuation, all kinds of other problems. So as I start dealing with moving signals through twisted pair cabling, all of my cabling should be 100 ohms. That's what the standard calls for. Okay, so I keep my cabling such that it's 100 ohms. Well, here's the problem. As I want to start increasing the frequency to get more bits through per time and increase the bandwidth, look what happens. When I look down here, I have resistances and reactances. As I start looking at the reactances, inductive reactance and capacitive reactance, part of those calculations, in here I see 2 pi FL. F is frequency, 1 over 2 pi FC, F is frequency. As I start changing the frequency that I'm using to get more bits through per time, I start whacking these numbers out, and eventually that's going to start whacking out my impedance. So what our cable engineers figured out, they're like, okay, if I want to start sending more bits through per time, I need to change something so that I can get that number back to 100 ohms and keep that at 100 ohm rating. Well, second side step, Mr. Brown. Oh, by the way, you don't need to know any of this. I'm just giving you a real life example of where the dilemma came from. Okay, so that's just kind of for FYI, for your information. All right, coming back here then. Example Mr. Brown's going to use. If I'm designing roads for a living, if I have a dirt road and I start driving cars on it, there's only so fast I can drive on that dirt road before my car's going to slide off the road. So we put a speed limit on there saying, hey, it's only safe to drive 25 on here. Well, if I want to be able to drive faster on that road, I have to change the, you got it, road structure. Maybe I need to pave it now. Yay! Now that it's paved, I can maybe do 45. But it's still a single lane road. I can't get more cars on. So if I'm going to get more cars on there per time, I need to cut down some trees along the side of the road and make it 2 lanes. Yay, I can get more cars through per time. What if I want to do even more? Well, now I got to start going through and making the corners not so sharp, and maybe getting rid of some of the hills, carving down some of the hills. Yay, I can go faster. if I keep going on that example, you start realizing how we get 2-lane highways, 4-lane highways, etc. And the structure of the road has to change for me to get more cars through per time, or to be able to drive faster on that road, which gives me more cars per time. Well, the same can be said about my cabling over time. As we went from category 3 and want to start putting more data through, the structure of the cabling needs to change so that I can keep it at this 100 ohms thing, and I can continue to get more bits through per time. Okay, so what happens now is the book gives us category 3, 4, 5, okay. They give us the frequency, okay. Let's take this a little further. If I start back in phone days, because this is where we start moving data around, dial-up modem phone days, my phone, I'm just reminding you, there's my phone cable. It's basically straight cable RJ11 connections. Okay. Well, what they found out was, as I start twisting these wire pairs together, the wire twisting does cancellation, which hopefully you remember, that cancels out and starts doing a little bit of like balancing out of the signal and allowing it to transmit better and kind of like self-shield some of the noise. I'm saying self-shielding, okay? So as we started off using category 3 cabling, we took the phone idea and started doing light twists on it to do that kind of self-shielding. And what they found was, hey, category 3 can support 10 megabit, 10 base T, 10 megabit, okay. We also know 5E, 6, and A can also do that too. That's why they're listed here. So my category 3 could do 10 megabit or Ethernet, plain Ethernet. Well, as we wanted to start sending more data through per time, crank that frequency knob up a little bit, the structure of the cabling had to change. As we go into category 5, what you see is that twisting is a lot more significant, and you actually start finding that the twist rates between the different color pairs here are slightly different. That way, the signals in the pairs don't affect each other. Category 5E was made with better quality copper and better twisting tolerances, so it could perform a little bit better. So as I look at my 5E here, I find out it was capable of 100 meg and even gigabit capability. 5E was actually capable of 100 meg and gigabit. Woohoo! That's why most places use category 5E and have been using it for quite a while. It's capable of gigabit to the desktop. Awesome. Okay. Well, as we wanted to start cranking up that frequency knob again to get my impedance back to 100 ohms, the cable designer said, okay, what we're going to do now is we're actually going to put a little plastic divider in between these wire pairs. And it's actually a little plastic divider, kind of reminds you of a plus sign, keeping these 4 wire pairs separated. I can't help it. I always think of the song "Keep 'Em Separated." Okay, anyway, now that we have that out of the way, it's keeping those 4 wire pairs separated so that again their signals don't affect each other as much, and I can increase my frequency. When I do that, I'm now capable of gigabit, even into I'm actually capable of gigabit, and as I move on to category 6A, which I'll show you in a second, I'm then capable of 10 gig. Okay, so going in here now to category 6A, I have the divider here, and I have foil shielding, or screening, sometimes you hear them called, screening around the 4 wire pairs. With category 6A now, I'm capable of 10 gig. I'm actually capable of 10 gig with the 6A. So the idea here is, the idea I want you to realize is, as the cable designers were learning and we were increasing the frequency, they're like, okay, we need to change the structure to be able to meet this increased frequency, to be able to keep the 100 ohm impedance, but able to carry more bandwidth. And with that, they developed these categories to label the side of the cable so that we know the structure of that cable inside is able to support, if it's category 3, it's able to support 10 megabit. If it's category 5, or 5E, it's able to support gigabit. Category 6 or 6A, we're now able to support 10 gigabit. Okay, that is what we should be taking away from this whole category idea that they introduced to us, and realize that we keep changing the structure inside of the cable to support this increased frequency and give us more bits per time, or give us this capability to do 10 gigabit, if you will. And the flip side is now going to be true. If a customer wants to be able to do gigabit to the desktop, we can get by with category 5E or 6. If they want to do 10 gig to the desktop, we're installing category 6A. That's what's going to happen. Okay, so we can use that to our benefit now. I'm going to come back in the next one and talk connections.